Okay, so here we are in Electronics 3. So if you recall last time, I sort of drew an atomic structure, and yeah, so I drew the carbon atom with 6 protons and 6 neutrons in the nucleus there in the middle, um, and it was sort of surrounded a lot of air and electrons, the 6 electrons in two shells, like you had the 2 and then the 4 outside in the next shell. So yeah, no. So the important thing to realise, right, is that electrons, they've got significantly. I did actually kind of say this. They have significantly more room. More room to move around. Than protons or neutrons. Okay, so yeah, and they can also be knocked out of their positions or completely leave the atom using far less energy than it takes to dislodge protons. To dislodge, I just put particles in the nucleus. So yeah, so protons and neutrons not going anywhere, but the unless you've got a huge amount of energy, but with electrons it's a lot easier. Okay, now as I've said, you've got the neutrons, which are neutral, and the electrons and the protons are charged particles. And yeah, and this whole thing with sort of force at a distance. So electrons and protons, and I'm going to be going through I'm going to be going through what I've said in the first 2 episodes as well. Electrons and protons are attracted to one another over a distance. So in all these experiments, with the with the wax and the wool, for example, you're seeing this opposing charge, which is creating an attraction. Yeah. Over a distance. There we go. And so what's actually going on when using, say, the wax and the wool is it's transferring, and the way it transfers, as what I said before, is actually going to be very important because it's not as because it's not as obvious as perhaps as it might be. Yeah. So, but for now, all I'll say is that so when objects are rubbed together, when certain objects are rubbed together, obviously exhibit these static electrical properties, and like I've said before, which ones did I say before then? Head and balloon, yeah, silk and glass, all this sort of stuff. These are the objects I'm talking about. When certain objects are rubbed together, electrons. So this was referred to as the fluid before. When I started, this is how it's actually started, and it was referred to as the sort of fluid. Yeah, at first I thought it was two fluids, then it was one fluid, but regardless, it seems to be a fluid. But this fluid is actually going to be the electrons. But yeah, when certain objects rub together, electrons move away from their. So yeah, it's quite interesting actually. From the original atoms, and reside around objects, atoms, and reside around the atoms of another object. Yeah. So that's what's going on. So yeah, I mean, it's just interesting to think. Yes, that is actually what's going on. The electrons are actually moving about just by doing this sort of this rubbing process, which you wouldn't, to move such a tiny. I mean, I suppose it's not particularly intuitive, I suppose, but that is what's going on. But yeah, and the reside around atoms another object. Yeah, but the question we need to think about is which way is this going? And we need to look at the forces involved. So let's so let's look at like the forces as a whole, and how these forces are going. So as I mentioned, like I said that I've said negative repels negative, positive repels positive, and positive and negative attract. So we can say that. In a different way, electrons repel each other over a distance. So each other over a distance. So negative repel. Protons repel each other over a distance. So positive and positive repel as well. Now protons, of course, are very different. Obviously, more massive. So yeah, now protons, they bind together in the nucleus. This is known because that doesn't need to be there, that little point there, because the strong nuclear force. So it's a very strong force, with a very high kind of I suppose separation energy, I think maybe. So yeah, but if you're going to want to break that bond, you're going to need a lot of energy. That's what I'm trying to say here. But of course, like I mentioned, electrons don't have these problems. They're just floating around, almost in a, they're in an atom, but they're a lot freer. Separation energy required is a lot lower. So yeah. But if electrons leave, or extra ones arrive, or extra electrons arrive, then the net charge of the atom is imbalanced, right? So it's imbalanced. Therefore, the atom as a whole is charged. There we go. This will cause it. This causes it to. Yeah, I'll just do like this. Don't want to do future tense really. This causes it to interact with charged particles. So yeah, so it's electrically active here. Charged particles and other charged atoms nearby. Okay. Yeah, and I may just I'll change the color again. We'll go back to this blue that I think I used in last time. Okay, so let's put some numbers in here. So yeah, so what I want to do is just do the conversion between conversion electron and Coulomb. Let's do that. All right. Put the N in there as well. All right. So 1 Coulomb is going to be an excess or deficiency, because we can go either way with the electrons. So that's this number here. Okay. So yeah, what number is that then? Let's see if I can work it out. So with 6 noughts, we've got 1,000,000. With 9 noughts, we've got 1,000 million. With 12 noughts, we've got 1,000,000,000. With 15 noughts, we've got 1,000 billion. With 18 noughts, we'll just assume they're noughts for now. 18 noughts is going to be 1,000,000 billion. Yeah, so that would be 1,000,000 billion. So I think that's 6,000,000 billion. Yeah, I think so. I think so. Obviously, using the whole 1,000 million, million. I would say that number is 6,000,000,000 billion, 6,250 million billion electrons. Okay. So anyway, so 1 electron has a charge. And now obviously we're going to have a very small number here. So we'll just do this. Yeah, I'm just going to write it like that. It's not. Yeah, well, I think the way to do it actually perhaps would be to do this section on the right here, the other way around, so it actually appears on the left, so that you've got nicely spaced 3 there. But I mean, that's a formatting issue. So we should have 3, 6, 9, 12, 15, 18 noughts there. Yeah. So you can see that these, similar sort of numbers here. Obviously 1 over that number. Okay. So anyway, so 1 electron. So this charge of 0.18016 coulombs is the smallest known carrier of electric charge. Yeah. Okay. And is therefore known as the elementary charge. Okay. So it doesn't get any more. Yeah, I mean it's the smallest carrier, so nothing can be smaller. Yeah. Well, I don't want to say that really, but yeah, it is the smallest known carrier, I suppose, occurring. So let's talk. Let's go back. I just want to sort of. It's going to sort of finish off this section here. So we've mentioned the imbalance of this fluid, right? Is so basically imbalance of this fluid, imbalance of electrons, or as we mentioned before, we did call it sort of a fluid here. Originally it was called that, and that is called static electricity. I mean, it's not used very much. There's only been a few machines that have used it, but yeah, I mean, but it is, you know, how I suppose it led to other things. And this word static, this word here, static, is used because the displaced electrons have a tendency to remain stationary. Okay. Okay. You know, after you move them from one insulating material to another. Okay. So now I want to. Now the final point I'm going to make is actually a very, very important point. And this final point is that it was basically thought, right? It was thought, as I mentioned before, it was thought that the electrons. It was thought the electrons in the wax go to the wall, right? But in fact, it was thought the fluid or electrons in the wax go to the wall. In fact, the reverse is true, right? It's thought, but no. In fact, the reverse is true, right? The wool, electrons in the wool. So why not? Electrons in the wool go to the wax. So this is the opposite. But wax charge had already been decided to be negative. So this was retained. So wax charge had been decided to be negative, to be called negative, and this was retained. Okay, so that was retained. Okay, so objects whose atoms have a surplus of electrons are negative. Object whose atoms have a deficiency or deficit, or whatever way you want to put it, are positive. So if we imagine atoms in some kind of generic object here, let's do it. I want to do an atom line. So numbers are going to be atoms. So we've got a naught here, +1, +2, -1, -2. So all this area here, this is positively charged. All this area over here, negatively charged. Well, I don't know if I should say all this area, but the point is, because obviously we're dealing with individual electrons, right? But yeah, we could say anyway, these points At the very least, we can say these points, -1, -2, positively charged, +1, +2, negatively charged. Okay, so that's all I want to say this time. So thanks for watching.